I'm very happy to be here at this conference, and so I would like to thank the organizers for the invitation. And so when I was a PhD student, I spent some time in Grenoble working with Laurent Bonaverot. And in this way, I got involved in a collaboration with Olivier and Stéphane Drouel. And so this then led to a paper by the four of us. And so I was very young, and I learned a lot, and it was an important work for me. So, okay, let's start. So, my talk is about Fano fourfolds, and I will start with an introduction. I work over C, and so let's consider a smooth Fano variety. We know that there are finitely many families in each dimension. And we have a classification up to dimension 3. And starting from dimension 4, we do not have a classification. And in particular, I'm interested in Fano fourfolds with large Picard number. So the Picard number since X is Fano, this is just a second Betti number. So it is a topological invariant, and it is constant in smooth families. So it takes finitely many values in each dimension. And so in low dimensions, we know very well the situation. In dimension 2, so these are the Pezzo surfaces. And we know that the Picard number is at most 9, achieved for the Pezzos of degree 1. And in dimension 3, so it's a result by Mori and Mukai as a part of their classification of Fano threefolds with Picard number bigger than 1, that for a Fano threefold the maximal Picard number is 10. But in fact we know more. If the Picard number of X is at least 6, then X is a product of a del Pezzo surface with P1. Fano varieties are simply connected, so the Picard number of the product is just the sum of the Picard numbers. So here we get rho x equal rho s plus 1. Rho s is at most 9, so we get a bound. Okay? Starting from dimension 4, we do not know the maximal Picard number. And if we look at known examples, all right. Well, we have, of course, products of surfaces. And with this, we get up to Picard number 9 plus 9, 18. And the others have Picard number at most 9. And in fact, in the last values, so 7, 8, and 9, I know only one family which is not a product. Okay, so somehow it's hard to construct examples of Fano fourfolds and in general in any dimension of Fano varieties with Picard number large. in fact, if you look at the classical constructions of Fano varieties, they basically all give very low values of rho. So I have a long-term project to study Fano forwards with large Picard number. So the expectation, as the examples suggest, is that the Picard number should be at most 18 with equality only for products. Okay. In fact, I expect a stronger statement that after some value lower than 18, you only have products of surfaces, like around 12 could be. This is just a guess. I have many partial results in this direction. Today I want just to present one. And yes, I also want to say that the goal of this study is not only to bound the Picard number, but if you want, the more optimistic goal would be to classify Fano fourfolds, say the first, which are not products, with largest Picard number, okay? From the point of view of classification of Fano fourfolds, this would be the easiest range with respect to the case of Picard number 1, which is probably the hardest, okay? But still hard. Okay, so the main tool that I use is birational geometry. In the framework of the minimal model program, and in fact, more precisely, by this I mean the study of contractions and of rational contractions of X. So let me recall what these are. So I will recall first the definition of a regular contraction, and then the rational case, which is less, I think, less known. Okay. So a contraction of X is just a surjective morphism with connected fibers where Y is normal and projective. Okay, and as usual, F can be birational or of fiber type if the dimension of Y is smaller than the dimension of X. And F is called elementary when the difference of the Picard numbers is 1, which are the easiest possible contractions. Okay? What is a rational contraction instead? This is a rational map. That Yes, I use Cartier divisors to define the Picard number of y. Okay. In general, it's not Q factorial. Okay, a rational contraction is a rational map that can be factored as a birational part, which is actually given by a finite sequence of flips, and then a regular part, which is a contraction. So this part is clear. I think it's what I already recalled. This is a birational map. X prime is projective, normal, and Q factorial, so it's not too singular. And this map is an isomorphism in codimension 1. Okay, so in fact, this is all I require on the map. And then since X is Fano, or more generally in a Moid ring space, you can always factor as a finite sequence of flips. Okay, so it's a more general notion. So if you want, the study of rational contractions of X is more or less the same as the study of these varieties, X prime, that you can get from X with a finite sequence of flips, and of their contractions, okay? Here everything is finite, so starting from X, you have finitely many X prime, and every X prime has finitely many contractions, okay? And also I wanted to say that this approach is very classical. In fact, it's what Mori and Mukai did to classify Fano threefolds with Picard number bigger than 1 was a study of contractions of Fano threefolds. The main difference with respect to dimension 3 is that in dimension 3, a Fano threefold has no small contractions, so there are no flips, so there is no rational contraction which is not regular, okay? In dimension 4, we have flips, starting from dimension 4, we have flips, so we have rational contractions. This makes things richer, if you want. There is more structure. Yes, so such a map is also called sometimes a small Q factorial modification. But I will not use this terminology, okay? So what I want to do is today I want to focus on rational contractions of fiber type. Okay, so this just means that the dimension of y is smaller than the dimension of x, and let me just note that x has a non-constant rational contraction of fiber type if and only if there exists a divisor D which is movable, non-zero, and non-big. So this is equivalent. Okay, so let me state the result I want to talk about. So we have a Fano fourfold. So if X has a rational contraction of fiber type F, and I need to exclude that the target is P1, so I want to y different from P1 and from P2. Then the Picard number of X is at most 18 with equality only if X is a product. Okay, So under this assumption of the existence of such a contraction, we get a bound that we expect in general for all Fano fourfolds, okay? I want to make a comment on this case. So asking that y is not P1 is equivalent to asking that y is not a curve. So I'm excluding the case of dimension 1 because x is rationally connected, okay? So if y is a curve, it's forced to be P1. So we are considering the case where y is a surface or a threefold, excluding the case of P2. Okay, so in the rest of the talk, I want to give an idea of the techniques that I used in the proof. So I will not actually prove anything, but I will give a sketch. And so the proof is also based on all my previous work on Fano varieties and on Fano fourfolds. So I chose to focus on the new part here. So now I will state a theorem that somehow is sums up what I use from my previous results. So I will just state it and use it as a black box. Okay, so I will not say, I will not talk about this. So let me call this theorem star, which is older. So we have x, a Fano fourfold. And then we have a variety which is obtained from x with a sequence of flips, as I explained before. And then I assume that I have a special prime divisor in x prime, which is dominated by a special family of rational curves, so by a family of rational curves Ct, and then I have two requirements on the curves. The first is that they have anticanonical degree 1, and then they have negative intersection with D. Okay, so I have this special prime divisor in x prime, which is related to my Fano fourfold by a sequence of flips. And then I consider the push forward of one cycle from an n1 of D to n1 of x prime. This n lower one are the vector spaces of one cycles with the real coefficients up to numerical equivalence as usual. Okay, so they have dimensions, the Picard numbers, and this is the natural map induced by the inclusion. Okay, so you take the class of a curve in D and you send it to the class of the same curve, but in x prime. And so if this map is not surjective, then either the Picard number of x is at most 12, or x is a product. Okay, so in particular this says that so the Picard number of x is equal to the Picard number of x prime. So when this map is surjective, this gives me information on the Picard number also of the divisor. Okay, so as I said, I will take this as a given, and maybe in the end, if there is time, I will comment a little bit on how this is obtained.
Is D normal?
No, no. In fact, what is relevant is only the image here, so I never really work with D. You mean with respect specifically to this or in general to this? So in the theorem about the contraction of fiber type, I really don't know about a singular case, even with my singularities. Okay. Instead, in this case, it may be possible to have a similar statement allowing some singularities, but still, I mean, very mild, like Gorenstein terminal, and maybe even locally factorial. Okay. So here, in this type of, in the computations that are involved here, Gorenstein is essential. Particular. Yes, but yes, so we say this. In X, I have a stronger statement. I can basically bound the dimension of the co-kernel here for every prime divisor. But the problem is that, in fact, I need to work in X prime, and in general, for any divisor, I can start basically with a divisor with a very large Picard number here, and then when I do flips, it becomes here very low. So in general, this statement in X does not give, for other divisors, it's just false in X prime. And for these type of divisors with these curves, what is useful is that I can get a statement in X prime. So, but the hard part is to prove it in X. Okay. Other questions? No. Okay, let's go back to the proof of the theorem. So we have a rational contraction of fiber type. But so in general, to work with arbitrary contraction of fiber type is very hard, because if you don't assume that they are elementary, the target Y can be very singular. Okay? So for this reason, I want to consider some different classes of rational contractions of fiber type. So let me say these are the general, all the rational contractions of fiber type. And then I consider a smaller class, which are special, which I call special. Rational contractions of fiber type. And then I have an even smaller class, which I call quasi-elementary. Same, a rational contraction of fiber type. And then we have the elementary case. Which is, as I said before, the difference of the Picard numbers is 1. These are the simplest ones. Okay? Okay, so in this case, so I don't want to explain, I will not explain what quasi-elementary is. I will come back to this a little bit later in the talk, but in fact in this case I already know the theorem because I proved it before some years ago. Okay? Okay, so what is new here to go from the quasi-elementary to the general case is this notion, special, which is the one on which I want to focus in the talk. Okay? So what I will do now is I will explain to you what is special, and later on we will see the difference with respect to this more restricted case, which is quasi-elementary. Yes, I also want to say that in this case, in fact, I have a stronger statement because I can also consider the case where the base is P1 and P2. So it's a stronger in some sense, but less strong in another sense. Okay, so I want to give this definition of special. It's actually very simple. I will first give it in the regular case for a regular contraction, and then we will see the rational case, but the essential case is the regular case. So let's consider a contraction of fiber type. It's called special. If so I have two assumptions. One is that the target is Q factorial, Y. And the second assumption is that concerns the image of prime divisors. So for every prime divisor D in X, the image has codimension at most 1. At most 1. Okay? So this means that either a divisor dominates Y, or the image is again a divisor. Okay? So basically, F cannot send a divisor to something of bigger codimension. So we are mixing two types of conditions. One is on the singularities of Y, and the other one, if you want, is on the dimension of the fibers of F. Okay? So for instance, so this definition makes sense for any projective Q factorial variety. Okay? So if X has dimension 4, the possibilities for Y is curve, surface, or threefold. Okay? If Y is a curve, F is always special. If Y is a surface, so say Y is Q factorial, okay? If Y is a surface, F is special if it is equidimensional. And if Y is a threefold, we want no three-dimensional fibers, and there can be two-dimensional fibers but isolated, no families. Okay. And then, yes. In the rational case, we just ask that our map, when we factor it like in the definition, the regular part is special. Okay, so a rational contraction of fiber type F is special if it factors as a sequence of flips and then a special contraction. Okay, so I chose to focus in the talk on this notion because I think it's actually very useful in the sense that on one hand, if your contraction is special and if you have good properties on the singularities of X, you need also some assumption of K negativity over contraction or log K negativity, then you get good properties on the singularities of Y. Okay? Similar to what happens in the case of an elementary contraction. So they give good properties on the singularities of the target. On the other hand, it's general enough that it's useful. And so in fact, the first step that I want to explain about the proof is the reduction, proof of the theorem there, the reduction to the case where F is special. Okay, and this is done because one can prove a proposition which says that if you have any rational contraction of fiber type, then there is a factorization So you can factor it as a first part, which is a special rational contraction. And the second part is birational. Okay, so basically this means that if our X has a rational contraction of fiber type, F, it also has a special one, okay? And the dimension of y hat is the same of dimension of y. So if we know that y is not a curve, this one is not a curve. And if we know that y is not P2, this one is not P2. So basically we forget about F and we work with this special part to prove the theorem. In fact, F is just in the assumptions, but not in the statement, okay? So here I've been vague in the about X, because X can be smooth Fano, but more generally you can take a Q factorial Mori dream space, okay? And the proof is a standard application of running MMP for the suitable divisor, so it's pretty much a standard result. Other questions? Okay, so this is...
It's not restricted to dimension 4.
No, it's not restricted to... It's very general, just a Mori dream space. Yes. Okay. No. Okay. So basically, now we are reduced to work with a special contraction. And now I will specify to the case of dimension 4. So we really have X a Fano fourfold. And we have our special contraction, and we know that y has dimension 2 or 3, and y is not P2. Okay? And then first of all, so of course I want to work with a regular map. So I will take a resolution of my contraction, like above there, flips followed by a contraction, okay? But in fact I can take a very nice one. So there exists a factorization given by a sequence of flips, and this is X tilde, this is F, this is regular, F tilde. So where F tilde is regular and special, and this we already know. And moreover, X tilde is smooth. And the contraction is K negative. So K negative just means that the anti-canonical class is relatively ample, okay? So this is really specific of dimension 4, okay? This is one of the reasons why it's easier to study Fano fourfolds. And I say a word because in a lot of talks people ask me about this smoothness. So if you have a flip, a K-negative flip on a smooth fourfold, there is just one type. It has been classified by Kawamata. And when you flip, you get another smooth fourfold. So even if you do many, you stay smooth, okay? And starting from dimension 5, this is false. So in fact, any flips I do, I always get something smooth, but then there is one choice, one good choice for which my contraction is also K-negative. And I will work with this map.
Is X still Fano?
No. As soon as I do a flip, it's never Fano. But in fact, it's possible to describe, it's very similar to a Fano variety. So you have to think that you mess up the Fano condition, but in a controlled way. So it's still very simple. I mean, it's very much related to X. Okay, so first of all, I want to describe the singularities of Y. Which are due to this nice setting. So if Y is a surface, then Y is smooth. This is because X tilde is smooth, the map is K negative, Y is a surface, and the map is equidimensional. This follows from the special assumption, okay? And then there is an older result by Andreatta, Ballico, and Wisniewski from the 90s, which says that in this setting the surface is smooth, and in dimension 3, Y can be singular, but very mildly, so Y can have at most isolated canonical locally factorial singularities. So in fact, these singular points can be only at the images of the two-dimensional fibers, okay? I said before that since the map is special, here we have dimension 4 and dimension 3, so the general fiber is a curve, it's actually a P1. And then we can have at most isolated two-dimensional fibers. And then the fact that in the images of one-dimensional fibers, Y is smooth, is also an older result by, I think, Mori in dimension 3 and then Ando. And then it's not difficult to see that also in the images of the two-dimensional fibers, you have controlled singularities. Okay, and in fact, it will not be very clear from the sequel, but it's very important to have knowledge about the singularities of Y. Okay, and then the key point of the proof is a study of prime divisors B in Y such that the pullback is reducible. Okay. So here I'm not, I really don't want to consider multiplicities, so I don't care about being reduced or not. I really only look at the number of irreducible components, okay? No? Okay. Now, since our map is special, we know that every component of the pullback of a divisor must dominate B. Yes, exactly, yes. I mean, there can be, but there can also be smooth points on the surfaces that are contracted. Yes. Yes. Okay, so we look at the prime divisors in the target, whose pullback has more than one component, and then each of these components must dominate the divisor, and then, so if the pullback is reducible, it means that every fiber over B is reducible, because it must have a component in each component of the pullback of B, but the general fiber is irreducible. So it means that there are at most finitely many divisors such that the pullback is reducible, because they cannot cover the whole variety. At most finitely many divisors. B1, Bm, EY, okay, so the case where m equals 0 means the case where the pullback of every prime divisor stays irreducible. Maybe non-reduced, but stays irreducible. And this, of course, is a special property, and it's actually the quasi-elementary case. So m equals 0 is equivalent to asking that f tilde is quasi-elementary. This means that the pullback of B is always irreducible. So this is not actually the original definition of quasi-elementary, but in any case I'm not giving it. So if you have never seen it, you can take this as a definition, okay? So in this case, in fact, we do not have to work because the theorem is already known. So what we actually have to do is to consider the case where m is positive. And where we do have these divisors whose pullback is reducible, okay? And then what one does is the study of the irreducible components of these divisors, which are fixed divisors. Yes. This. Okay, but I'm using the fact that I already know. If you want, I take for granted the theorem in the quasi-elementary case, which is the case m equals 0. Okay. So I have the irrational contraction of fiber type. I replaced it with a special one. Okay. And then I take this factorization and I work with this f tilde. Okay. And what I was saying is that these irreducible components of these divisors are actually the key point of the geometrical study here, and they are fixed divisors in the sense that they don't move, and also the multiples, they don't move in the linear systems, okay? And now the proof is different in the case of dimension 3 and 2, and I want to give an idea of both cases. Let me write here. So, the case of dimension where y is dimension 3 is easier. And the easiest case is if m is at least 2. So I explain this one. So in this case we have at least 2 divisors in y whose pullback is reducible, okay? But then it's easy to see that the general fiber of f tilde is just a P1. With anti-canonical, and the fiber has intersection 2 with minus k, because basically where the fibers are one-dimensional, this is a conic bundle. Okay. So if you have a fiber which has dimension 1 but is a reducible one-dimensional fiber has at most 2 components. Because minus k is relatively ample, everything is smooth, so 2 is at most 1 plus 1, okay? And so this means that the pullback of these divisors has 2 irreducible components. Say EI and EI hat. Let me draw a picture. So here we have y, and we have, this is the general fiber of x tilde, okay? And then we have one of these surfaces, special surfaces bi, and the pullback has 2 components, which are generically P1 bundles over the base, and then they may have some 2-dimensional fiber somewhere. okay? So this is a reducible pullback, okay? Right. And then, so we have two points here. So if we look at a general fiber of f tilde over bi has a form, so it will be reducible. It will be basically a reducible conic. So the two curves are P1. They have intersection 1 with the anticanonical class. Okay, and they are contained in the two irreducible components. Okay, so this is, say, fi and fi hat, the two curves. Okay, but then you see that, for instance, ei has intersection 0 with the general fiber, and this is equal to the sum of the two intersections. Okay, this one is positive because fi hat is in the other component, so this one is negative. Okay, so I found a prime divisor which is covered by a family of rational curves, and these rational curves have intersection 1 with the anticanonical class and negative with the divisor. This is precisely a divisor like this D here. Okay, so I have the first part of the assumption on the family of curves, but I still have to check the second part of the assumption. Okay, I want to apply this theorem star. Okay. So up to here I did not really use that M is at least 2, but then if I have at least 2 of these divisors, so it's actually easy to show at this point that these surfaces in Y, the BIs, must be disjoint. So if I assume that M is at least 2, then I have at least 2 surfaces whose pullback has that form, and then it's easy to see that they cannot meet, basically because otherwise these two, the curve classes should coincide, but this is impossible. And then also the divisors upstairs will be disjoint. So I'm taking E1 is one component of the pullback of B1, and E2 is one component of the pullback of B2, no matter which ones. And then we are done, because this means that for every curve C in E1, the curve has intersection 0 with E2, so the class of this curve belongs so in N1 of X tilde, numerical classes of 1 cycles, I look at the hyperplane of classes which have intersection 0 with E2, okay? So all the curves in E1 are in this hyperplane, so the push forward of N1 of E1 is contained in this hyperplane, and so it's not the whole N1 of X tilde, and so we conclude by theorem star. Which says that in this situation, either X is a product or the Picard number is very low. Okay. Okay, so let me just say a word on the case. The remaining case where Y has dimension 3 is M equal 1. And this is the less interesting case, but longest, because what I do is I check that I can redo the proof for the case M equals 0. So it's a boring case, but in the end it works, okay? And I wanted to comment that when the base has dimension 3, in fact, the proof gives a much stronger statement, because if X is not a product, the Picard number is at most 12, okay? I need such a more general statement for the case where Y is a surface. Okay. Okay, let me just say a word in a minute about the case where Y has dimension 2. Because then you see why I need to exclude that the base is P2. So in this case, BI B1 is a curve. Okay. And then one study its pullback. And there is a part which I don't show, which is a hard part, is that you show that one of the components of the pullback still have this family with this special property. So say fact, there exists a component D of the pullback of V1 with a covering family of rational curves which have intersection 1 with the anti-canonical class and negative with the divisor. Exactly like the divisor E1 there, and exactly as in the assumptions of the theorem here. And then exactly as before, I want to apply theorem star, but I need to check this other assumption that the push forward of 1 cycles is not surjective, but this is easy when Y is not P2. Because I consider the push forward of 1 cycles given by F. Okay, so this is a surjective linear map, and yes, I want to look at the images of the curves contained in this divisor D. So if gamma in D is a curve, so the image of D is this curve P1, B1 in Y. So we have either f of gamma is a point, f tilde, or f tilde of gamma is a curve B1. So when I look at the push forward of the class of gamma, gamma. This is either 0 or belongs to the line spanned by the class of B1, so in any case it's in the line, okay? So in the end, the image of the N1 of D is equal to this line. Okay? And so here we need to exclude the case of P2 because, so here if the Picard number of Y is bigger than 1, then this equality implies that this subspace is strictly contained in N1 of x tilde, and you conclude by theorem star. Instead, when the Picard number of y is 1, we cannot conclude, we cannot apply theorem star. So y is a smooth rational surface with Picard number 1, so it's P2. Okay. Okay, thank you. I will stop here.